So if I have a vector field defined by y 3z minus 3z minus 5x, okay, so this is a vector field. And then we want to look for all the forms of the vectors such that if I do the dot product between this vector and the curl of this vector field, it is equal to 0. So find, and that's basically what the question is asking. So we have a vector field. So doing the curl, you're getting another vector field, right? So now we're looking for the other vector such that the dot product between these two is always equal to 0. In other words, I'm actually using an n here to denote the unknown vector. In other words, I'm looking for all the normal vectors to the curl vector field. Am I right? Because if you do the dot product, you're getting a 0. This is essentially saying these two vectors are orthogonal, right? So essentially, this problem is asking you what are the orthogonal or normal vectors to the curl of a vector field. Okay? So even though this question seems intimidating, but at least I know there's some points I can grab, which is computing the curl. Even if you have completely no idea what curl is, but as long as you remember the formula, you should be able to at least get some point. So the curl of the vector field is equal to I, j, k, partial x, partial y, partial z, and y minus 3z and minus 5x. So Jonathan, is Jonathan here? Okay, so let's do the curl of the function.
All right.
So the I component is
Partial y.
partial y hitting on minus 5x, you're getting on
Negative 5xy.
not really. This is just taking a derivative with respect to y.
I integrated.
You don't have nothing.
0.
It's 0 minus partial z hitting on minus 3z.
Negative 3.
Minus 3. Okay? So that's our I component. J component is going to be partial
Z.
z hitting on y.
0.
0. Partial x hitting on this one.
Negative 5.
95 is 0 minus 5. And then the k component is partial x hitting on minus 3z.
0.
0. Partial y hitting on y.
1.
1. So in the end, this curl is nothing but 3, 5, and 1. Okay? 3, 5, and 1. So if I want to find the form for the normal vector, so let's assign some letters here. So if this normal vector is equal to a, b, and c, okay, then the dot product between these two vectors is equal to 0, is equivalent of saying 3, 5, and 1 multiplied by a, b, and c is equal to 0. Right? Now you have 3 unknown variables, only one equation, which means 2 of them are given freely, and the other one will be deduced by the other unknown. All right? So if you have 3 unknown variables, we have been playing around with this quite a long time. You have 3 unknown variables, one equation, then you can choose A, B freely, C will be solved by this equation. All right? So basically, this is 3A plus 5B. Oh,
Shouldn't that be a negative 1? Should be a negative 1.
Minus 1, right? So partial x hitting on minus 3z, I'm getting a 0 minus partial y hitting on y should be minus 1, right? This one should be minus 1, which means minus c is equal to 0. So we have the form which is a, b has 2 free variables, and c has to be of the form 3a plus 5b. Okay, will be our answer here. Okay. Questions? Okay, so if no, we're going to move to our next section, which is reading the preparation for all the following work. That's why it is extremely important here. Okay.
How would they ask you this question?
I'm sorry?
How would they ask you this question?
So the question is to find the normal vector of the curve, right? The normal vector has the property that if you do dot product, you're getting 0. So we want to do section 15.6, which is surface integral. Okay, surface integrals. Because now we want to do calculus in our 3. So instead of doing the line integral, we have to do surface integral. Right? I give you the motivation of considering surface integrals. Surfaces are the boundary of solid region in our space, so we have no choice but to do the surface integral here. So I wanted to quickly recall the line integral because these two are quite similar. So if I have a curve, so this curve is defined by RT is equal to XT and YT, okay, which is the parametric equation of the curve. So every time if we have a parametric equation for a curve, we always ask for the range of the parameter. So t goes from A to B, right? So it's the initial time and the term. And the other thing I want to be very clear is a curve is a one-dimensional object. You only need one parameter, right? Either you have a line or a smooth curve, but in either case, this is just a one-dimensional object. It is the one-dimensional object. It's because you only need one parameter. Okay, basically that's the reason. If you can parameterize an object by only one parameter, this object has to be one-dimensional. Okay, and also we will be able to do the following. We can do the line integral along the line of a scalar function, right? We can do the line integral of a scalar function along the line, and remember the formula says this guy is equal to from A to B, f xt yt, and then multiply by the tangent vector element right here, okay, right? So we have a r prime of t in length and then dt. So this is the factor we have to include when we do a line integral of a scalar function. We can also do the line integral of a vector field. Actually, we have two forms to do. One is to the line integral of a vector field along the tangent direction, which you need to do the dot product between the vector field with the tangent vector. All right? This is one of them. You have a particular formula to evaluate what this is. We also include the line integral of a vector field along the normal direction, all right? Along the normal direction, which you need to do the integral between the inner product of the vector field and the normal vector, all right? So we also have the two names for these two line integrals of vector field. First one is circulation. Second is called flux. Okay? So we have a line integral of a scalar function, line integral of a vector field along the tangent directions, and the line integral of a vector field along the normal direction. So there are essentially three things. So I want to generalize this line integral into surface integrals. The very first job we have to do is to get this parametric form of surfaces. Okay? Given any surface, we should be able to derive what the parametric forms are. In other words, at least I have to have parameters. Because if it is a curve, essentially it's a one-dimensional object. You only have one parameter over here, right? If you want to parameterize a surface, you need two parameters. You need two parameters to describe a surface. So that's the main difficulty generalizing from a line integral to a surface integral is to find the parametric equations for a given surface. So what are the surfaces we learned before?
A lot of them.
Sphere, circle is a line, essentially, right? So we have a cone, paraboloid, ellipsoid, and all those kind of things, right? These things are cylinder, these kind of things are surfaces. So we want to have the parametric equations. So this is the most important thing. And also x, y, z equation. Okay? So parametric equation, we needed two parameters, and usually people prefer to use u and v as the two parameters. Okay, so just as what we did for the lines. For line, I have two things. One is the xy equation. The other one is the t equation, right? So like the very popular example, in xy equation, the circle is written down in x squared plus y squared is equal to radius squared, right? And in the t equation, we have r cosine t and r sine t for the parametric equations. So if we have two different equations to describe the same object, and I also mentioned there's something more in here, which is what's the parametric equation producing more in terms of describing the curve? The orientation, right? So this guy actually gives you the orientation, which the xy equation doesn't give you. So in order to link between these two equations for the same curve, we should be able to do the following two directions. First direction is I can go from the t equation to get the xy equation by eliminating t variable. What did we do? This is essentially equal to x. This is essentially equal to y. If I want to eliminate t, what do we do? X squared plus y squared, you're going to eliminate cosine and sine simultaneously, right? So in one direction, in order to get the xy equation from the parametric equation, you need to eliminate the parameter. If I go from the other direction, if I have xy equation, I want to get the parametric equation, I need to assign a proper rule for the parameter, right? You have to introduce this new parameter, but what rule do you assign? And if you have a circle, you assign t as the rule, so this is the angle essentially, right? So this t is the angle, so cosine t times r is the x variable, sine t times r is the y variable, okay? So we have to be able to go from both directions, from xy to the uv direction. So from xyz equation to the uv direction, we need to introduce two variables, u and v. What rules do we assign them? If we go from uv direction to xyz direction, what do we do in order to eliminate both of the two parameters? How do we eliminate both of them in order to get x, y, z? Okay, so I'll give you a couple of examples to begin from. So let's say if I have this equation, a cosine u, a sine u, and v. Okay. So apparently this is the parametric equation for something, but then I need to realize what this thing is, what this surface is. Okay, so we have a UV equation. Because we're so familiar with, hopefully you are so familiar with x, y, z equation. So one thing you can do is to eliminate u and v and see what kind of x, y, z equation you get. All right? So this is essentially x, this is y, this is z. How do I eliminate the u and v? How do we eliminate u and v?
Squared.
Just squared it. That's exactly what we did here, right? So if I look at x and y component, I know x squared plus y squared is going to give me a squared, right? V, unfortunately, is completely by its own. It's a real free variable. Has nothing to do with x, has nothing to do with y. And this is the case where this equation does not even contain the z variable. This guy defines when you don't have any z variable in here, what does it define? If your equation is missing one variable of the x, y, z, that equation defines a
Plane.
cylinder. All right? The equation defines a cylinder. If you have an equation does not even contain z, z has nothing to do with x and y. This equation defines a cylinder, remember? So on the xy plane, this defines a circle, and then in the z variable, you just pull it. Because it's completely free. Oh yeah, that's true. Right? Cylinder is the case where your equation does not even contain one of the variables. And that variable is completely free, so you can pull that freely in that direction. Okay? So this one defines a cylinder in the z direction. So I have xy circle, and then this is where the cylinder is. Okay? So this is the x squared plus y squared is equal to a squared in the XYZ equation. So I will be able to do from the UV equation to XYZ equation. Okay? So this direction is already fixed. How about the going from XYZ to UV and UV equation? Then I want you to understand that these three equations is a very natural choice. If I have this equation define a cylinder in XYZ space, then definitely I want to introduce x to be equal to a cosine u, and y to be equal to a sine u. And this is a very proper rule when you assign the parameter u. All right? And the v to assign to a row of z, because z is completely free. Right? It is completely free, so the only rule you can assign for the remaining parameter is to assign v to be equal to z, and that's it. So this is going to be the parametric equation for our cylinder. So your brain is programmed for x, y, z equation. From now on, I want you to be as sensitive to this parametric equation to this kind of equation as well. Okay? So imagine if we begin from this equation and we agree this is actually the equation for a cylinder. Then you look at this kind of equation, you might be very strange. Right? Overall, you should be able to do both directions. Okay, now I want to mention one thing. Every time I have a parametric description of a surface, I also should have the restriction or the range for the two parameters. Okay, right? I should have the restriction of u and the restriction for v. V in this case is basically talking about the height of the cylinder. Right? So if I make z equal 0, I'm getting the circle right here. So if v is going from, let's say, from 0 to h, if v goes from 0 to h, I need to cut the cylinder below xy plane and cut the cylinder above h. So then I'm going to get a bounded surface. So v is talking about the height of the cylinder, and u is talking about the rotation along the axis. Okay? So if my u is going from 2 pi to 0, and v goes from 0 to h, I'm getting a piece of the cylinder from xy plane to the height of h. Are you with me? So this is basically the restriction can tell you. Okay? This is the restriction can tell you.